Good morning, guys. Welcome to Bidance Online Academic Tutorial. Thanks for watching our videos today. Today, I'm going to be talking about Waec chemistry practical in anticipation for the upcoming exam, which is 2024 Waec GCE. And before me is a chemistry past questions on the first question on chemistry practical, which is volumetric analysis. This is an alternative to practical questions that we are going to gather in November, December questions. And the first questions is actually on titration. In a titration experiment, 10 centimeter cube, which is the volume portion of 0.15 dm cube mole per dm cube, solution of potassium triazocarbonate 4. Potassium triazocarbonate 4. The potassium triazocarbonate 4 can be written as K2CO3. That is the formula, the chemical formula for the compound, and we are told that the volume for heat actually this is actually known as a weak base. It's actually taken as a weak base, which is a weak base because it actually has a pH of around that of its pH is very close to that of 7, around 10, 11. So that's why it is called a weak base. So now it has the volume, which is, I'm going to represent the what usually base usually represented by B, and then so I will represent the volume as VB, which is equal to 10 centimeter cube as given in the question. So, and then the concentration is mole per dm, that is CB. The concentration is represented as CB, which is equal to 0.15 mole per dm cube. 0.15 mole per dm cube. And then was titrated, meaning that this is a base which was pipetted and then was titrated with tetraosulfate 6 acid, which is our acid A, which is tetraosulfate 6 acid, H2SO4. And then using methyl orange, our indicator is methyl orange here. The indicator use is methyl orange. Please take note of that. The result recorded is shown in the table below here. This is the volume 1, V1, this is V2, and then V3. So now we are now told that this is the volume, and we have to complete the table. The first thing is to complete the table. You can see the first entry here is 14.45, and then the starting volume is where the meniscus was like. Now this is the volume that was used, while the burette is actually at, when they fill the burette, it was actually at 1.80. It does not start at 0. Like when you draw a burette, this is how burette look like. But you don't need to know all this for alternative to practical. For alternative practical, I just want to let you understand what it means. So assume this is 0. Assuming this is 0.0. Actually, the 0 is, the 50 will be here. Yeah, the 0 is here. If I could remember very well, the 0 is here, and then we have our 50 here, or whatever the case, or the 0 here, 50 here. So meaning that what, this does not actually get to meniscus of 0. It actually starts with what? It starts at 1.8, or the liquid, the acid that was poured in the burette starts from 1.80, and then what was used, the acid that was used is between 1.80 and then 14.45. I told you that the burette is actually from 0 to 50, but they didn't feed the burette to 0 brain. It was filled to 1.0. That's what this one means. And then the amount that was consumed for the titration for V1 was between 1.0 and 14.45. So to actually get the volume, actual volume, you are going to subtract 1.8 from 14.45. It's just as simple as that. I just wanted to get to the logic, so I might not repeat that again. So this one will be 14.45 minus 1.80. So we have 12 points. So here we have 12. We have 12.6, 12.65 as the volume that was used. Then here we are told that 12.15 was used. So to know the actual volume here, we just add this one together. So 14.45 plus 12.4 12.15 12.15. That is when you add this together, 14.45 and therefore you get what? 26.6. So, and then the last one here is we are given a specific volume here that was used, but we need to provide this one. All you just need to do is subtract this one from this. That's 38. Remove 12.05 from 38.65 to get your missing value here. 38.65 minus 12.05. So we have 26.60 here, 26.60, 26.6. So make sure it is 2 decimal place, please. Very, very important, because you have it in 2 decimal place, 36.65, 14. So your answer must not be in 2 decimal place. So now you have completed the table, but this table must be transferred into your partial booklet. But in the case of alternative to practical, you are going to submit the question, the answer in the answer booklet. So probably you are going to be writing on the you are going to be writing the question by itself. So you are going to be writing on the question by itself. But in a place where you are given an answer, you have to transfer this table and then copy it in a new fresh page and then put all your answer into it. So now calculate the average volume. Now next thing is to calculate the average volume. Average volume will be equal to the 2 concordant values. You cannot just use any values. You must ensure that you use the concordant value. Like the first one is 14.45 minus 1.80, and we get, I want to check that one again because it's very, very essential to confirm your answer. We can still get 12.65, and then we also get 12.15, and we also get 12.0105. So you can see these 2 values are the most concordant values. This is very far, this is not concordant. So this I expected to what? You are not expected to use this one because the difference between this and this is around 0.40, but difference between this one and here is just 0.10, 0.10. So these are concordant values. So you are expected to use concordant values for calculation of the average volume of an acidule. And what makes something concordant is that the difference must not be more than 0.2. The difference must not be more than 0.2. So that's the difference. So the difference between here is just 0.1. So that's why it's a very concordant. So I'm going to be using what? The volume 2 plus volume 3 as my 2 concordant value divided by what? 2. That's how to find the average. Because I'm using 2 volume, I'm dividing by 2. So I'm going to be using 12.15 plus 12.05 in centimeter cube divided by 2. So we have 12.15 plus 12.05 divided by 2. So we have 12.10. So we have 12.10. When we add this one together, we get 12.10. So the volume here is 12.10 centimeter cube. Please note that 2 decimal place. It's very, very important. 12.10 centimeter cube as the volume of an acid, average volume of an acid use. So coming back to what the Roman figure 2, this Roman figure 1 question. Roman figure 2 question says that the average data, we have done that. The equation answer says, okay, calculate that, we have done that. Okay, the equation of the reaction between these, you can see the equation of the reaction is this: K2 plus H2SO4 to give and this and this. You can see the reaction give salt. This is the arrow here. The arrow is supposed to be here. It give salt and then CO2 and then water. So from the information provided and your results, calculate the concentration of acid in mole per dm cube. The concentration of acid in mole per dm cube, that is Ca. Concentration of acid in mole per dm cube. Concentration of acid of A, which is concentration of A, which is H2SO4. Don't forget H2SO4 in mole per dm cube. You have to take note of that. That is very, very crucial. Mole per dm cube. So now, and what you do is this. What you do is this: is that you look at the parameter given to us. How will I get concentration of A in mole per dm cube? And it's very straightforward because all the information seems to have been given directly. Because if you look at this, we have the concentration of B, we have the concentration of B in mole per dm, which is 0.15 mole per dm cube. We have VB, volume of base used, which is 10 centimeter cube. And then we have to calculate Ca. Very straightforward question. We have Ca using the formula Ca over CAVA over CB, VB equal to Na over Nb. So this is the formula we're going to be applying. So we are looking for Ca multiplied by the volume we've gotten is volume of acid used from the average data now is 12.10 all over Cb. Cb is 0.15 multiplied by 0.15 multiplied by 0.15 multiplied by Vb. What is Vb? Vb is 10 centimeter cube. You can see upstairs there. So Na, which is very, very crucial. Look at A. I told you that A is acid, which is H2SO4, and B is base. So you can see the mole ratio here is what we call Nb. I take the Nb, and this one is supposed to be Na. So the ratio of K2 SCO3 and H2SO4 are in 1:1. Look at it, they are balanced in 1:1. K2SO4, CO2 is coming out, then H2O. So this is 1:1. Na, the ratio of acid, number of ratio of acid to base is 1:1 because this is gotten from the balanced chemical equation. If it's not balanced, you are expected to balance it. But this one is already balanced. You can see 1 mole of H2SO4, 1 mole of K2CO3 reacts to 1 mole of H2SO4. So there's nothing for you to do any balance here other than to just put 1/1. So please note that very, very important. It's very, very important. So it's very, very important to know K2CO3 plus H2SO4. They react to each other in 1:1 to give salt and water and then carbon dioxide. Salt, water, carbon dioxide. So they react in 1:1. That is, this is A, this is B, this is A. Even they are just 1:1. So that's the most important thing. So in cross multiplication, what we have here, when you cross this and this, we are going to have something like this: Ca multiplied by 12.10 equal to 0.15 times 10. So times 10, yeah, times 10. So divide both sides by 12.10. 12.10. 10.10. So this one cancel out. Then when you press your calculator, what do you have? 0.15 times 10 divided by 12.10. We have 0.1239 mole per dm. Let me zoom it back. And then bring this. So trying to I just move a little bit forward. Okay, so that's what we have here, but approximately got 2 decimal places because the first one was in 2 decimal places. If I approximate this one to 2 decimal places, you're going to have 0.12 mole per dm cube. So CA here is going to be approximated to 2 decimal places. Now let me CA constitution of A, because that's what we have. So the constitution of A in mole per dm cube will now be what? CA to 2 decimal places will be, when you approximate to 2 decimal places, that will be 0.12 mole per dm cube. So mole per CA equal to 0.12 mole per dm cube. So that is that about that. So for question roman figure 1B, roman figure 1, that is for B, roman figure 1 for B. So now the next thing is to actually now calculate the mass concentration of potassium tetrasulfate 6 that would formed in solution. The mass of tetrasulfate 6 that will form in the solution. What is the mass of tetrasulfate 6 that will form? So this is very important to write the balance equation. So I will quickly write the balance equation here. Let me change the color to the question I'm answering now. So we are having K2CO3. That's from our 3 question. Starts here. We have to go 2B, we have to go 2 here. K2CO3, because you need balance equation here. H2SO4, H2SO4 to give K2SO4 plus CO2 plus H2O. Maybe you don't need it, but let's write it out first. So I told you it's a ratio 1 to ratio 1, 1 to 1 ratio, so there's no need for us to balance it anymore. So the first thing to calculate the mass form in solution is they are asking you mass concentration, mass of potassium tetrasulfate 6 that will be formed in solution. So what we'll do is that we have been given base to be what? To have molar concentration. The molar concentration of B, which is I tag this one B, don't forget this one is what? A. And the molar concentration given to us is 0.15 mole per dm cube. This is molar concentration or concentration in mole per dm cube. So what you need to do is to calculate the molar mass of this, because to get the mass form, what they mean by mass in solution is that you are going to get mass concentration. The reason why you can go to get mass in concentration, it means that mass over volume. And mass over volume, what they mean by mass of potassium tetrasulfate that will be in solution. It means mass over volume. That's what it means. Mass over volume. That's what they mean by mass of K2SO4 in solution. It means mass over volume. So meaning this is mass concentration. It's same as mass cost, and this may also mass concentration is same as mass over volume, which can also be calculated as molar conc. I'm giving you the formula now. Multiplied by molar what? Molar mass. Molar conc multiplied by molar mass. Molar conc is what we have been given a conc. This is molar conc here. This is molar conc here. Molar. This is molar conc here. This is molar conc. Molar concentration, which is also known as concentration in mole per density. Now you need molar mass, and to get that molar mass is that's why you have been given this. O is 16, S is 32. Molar mass is just from the formula of molecular formula of what K2SO4. So I want to calculate the molar mass here. Molar mass of K2CO3 will be 2 into bracket potassium is 39, I guess. Yeah. Plus 3 into bracket 16. Wow. So this one will be what? 2 into bracket 30, 2 into bracket 39, 2 into bracket 39, 2 into bracket 39. Plus 12 plus 3 plus 16. 138. So 138 gram per mole. 38 gram per mole to back 39, 12 plus. So we now have molar mass. We have, so we do now is just put everything 0.15. That's molar conc times 138. Change back. That's what we get for the molar mass of this. So multiply by 0.15. So we have. So we have the mass that will be here will be 20.7 per dn cube. That's the mass. But the mass 1.7 gram of K2SO4
dissolved or was in solution of 40 true with this. So that's what this question is about. So now the next one is list 2 techniques that could be used to recover potassium tetrasulfate from solution. Is a salt? This is a salt. Let me use another color so that you can know the question. Okay, let's pick another color here. Let's pick blue. Okay. He said, what technique we use to recover potassium from solution? Is K2SO4 is a salt, as I said you earlier on. It's a salt and it's a weak salt. It's actually a weak base, also known as normal salt. So it acts as a base, and it's also a very it's also a salt. So it's actually for you to know that it has a double properties. So it's actually used as a base, but it's actually a salt, a normal salt. So it can act as a weak base as well. So K2SO4 in water, when you dissolve it, it actually dissolves. It dissolves completely in water. It forms like, since it's a salt, it actually forms a colorless solution. It forms a colorless solution. I'm just drawing it. So this is what? This is the dissolved solution of what? K2SO4 of K2CO3. Here we have K2CO3. This is a dissolved. It's totally dissolved. A colorless what? It forms a color. It is taste salty if you taste it, but this is a base. It will not taste
salt, it might have the element of base, like it might be soapy, but not that actually. So because the colorless is not that, it's not as actually strong. But what I'm trying to say is that the most important is that a discolorless solution, it will dissolve. It will look like water completely, or sometimes it might look a little bit cloudy, but it will completely dissolve in water. So to remove this thing, to save our time, is to what? Actually eat it. You eat it, you put it on Bunsen burner, expose it on Bunsen burner, or yeah, you can expose the Bunsen burner to actually heat evaporation. Evaporation, very, very crucial here. Evaporation or crystallization, because it's also a salt. Aspect question. You said, okay. Solution of what? The two in one question. Wow. We use this one to actually, okay. A solution of acid containing this each 500 centimeter cube, that is A. Okay, can I clean this so I can create space? Because it's an entire question, it's a new question entirely. So let me quickly clean this. Create a space for it. So
tutorials to actually see the practicality behind these questions. If you're able to control it and have the understanding of what is going on, then almost time you can still understand this based on what I'm explaining. But if you want to see the practicality, you can actually look for practical on volumetric analysis on my YouTube channel. So VB equal to 2 centimeter cube, which is the volume of the base used. So this is the concentration CB, which is 0.1 mole. I just want to emphasize this. So this is VB, that is the volume, this is the concentration of the base. This is the word volume of the base. So using a stable indicator, now they told us that they use a suitable indicator. The first question now is now name an indicator that is suitable for this reaction. Now the first thing is to identify what type of reaction is this and what indicator is suitable for it. Now when I talk about indicator, we are talking about reaction that is between acid and base. We usually use indicator for acid and base. So usually for acid and base reaction, that is neutralization reaction. And what type of acid and base is involved here? You can see it is a reaction between strong acid and strong base. This is, let me continue right here. HCl plus sodium hydroxide. This is a strong acid. It's a strong, and this is a strong base. So to give NaCl plus water, it's a neutralization reaction because you only have salt and water. So now, because it's a strong acid and strong base, actually require any suitable indicator, but you cannot write any suitable indicator, any indicator will be suitable for this. Any indicator will be suitable for this. So when I mean any indicator, that is, whatever indicator you are going to use is going to be suitable for this, because strong acid and strong base doesn't require special indicator. Any suitable indicator will do this reaction. So, but you need to mention it in particular. You can even mention the methyl orange. One, I can decide to use methyl orange or methyl red. Methyl red. I can use phenolphthalein. Phenolphthalein, this is N, this is phenolphthalein. I can also decide to use crypsin and so on and so forth. There are other type of indicator, but these are the expected one: methyl orange, methyl red,
phenolphthalein. These are the three most popular ones that they are expected in Waec. So state the color change of the reaction at the end point. Now, this is very, very crucial. When you have a base, the base will enter first. You put base inside this place. What you are going to get, it depends on the indicator you wanted to use. If you suggest, you must know how methyl orange works. If you suggest phenolphthalein, you must know how it works. So now you have to be vigilant. So if I'm going with methyl orange or methyl red, you must know what to get at the end of the day. Else, you are going to lose your mark. Like this one now, methyl red or methyl orange actually have yellow, then pink. This also have yellow, yeah, you have yellow, then pink or slight orange. So, for instance, now if I'm using, let's say I'm using methyl orange or methyl red, methyl orange, or sometimes methyl red. What I'm going to, if I put the indicator like it looks like this, in a bottle, and I drop the indicator in base before adding my, if I add this indicator in the, you are going to get for methyl orange, you are going to get, initially you are going to get yellow, then later you can get orange at the end point, or you get slight reddish orange. For methyl orange, you get what? At the end of the titration, you get slight. So you have what? Methyl orange. You have orange color at the end point, or red or pink. Now, get it right. If you are using this red, methyl red, you are going to get pink. The end point, this one is going to give you pink. This one is going to give you what? Reddish orange. Reddish orange. This one is going to give you pink. And this was colorless at the end point, colorless solution. This one is going to give you colorless at the end point. Note that this is pink, and this is going to give you pink for methyl red. This one will give you colorless for phenolphthalein at the end point, and this one is going to give you reddish orange for strong acid and strong base. Note that. For strong acid and strong base at the end point. Look at it. They didn't say in acid, they didn't say in base. At the end point. At the end point, methyl orange will give reddish orange. At the end point, this one will give you pink. At the end point, phenolphthalein will give you what? Colorless solution at the end point. Don't the word end point. So it's very crucial. Then the next one, the last one, which is this one, which is calculate concentration of A in mole per dnq, concentration of A in mole per dnq, concentration of A in mole per dnq. But we have already seen the balance equation. Actually, the next one should be what? The first one is we have written out the formation, and we have indicated the indicator, that is the Roman figure 1. Roman figure 2, then another color, Roman figure 2. Is state the color change for the endpoint. I've already done that. State the indicator suitable. I said indicator that is suitable. You can write any of these three is suitable for this. Why? Because it's acid, strong acid, and strong base. You can either use methyl orange, methyl red, or phenolphthalein. And then the question says state the color change at the endpoint, meaning that the indicator you picked. The question says an indicator. You are expected to tell them one of this indicator. As we have told them that I'm using phenolphthalein now, I'm expected to talk about the color change at the end point. And the color change for phenolphthalein will be just the color solution if I'm using what? Phenolphthalein for colorless at the end point. Colorless at end point for phenolphthalein. Colorless at end point for phenolphthalein. But for methyl red, it's going to be pink. For methyl orange, it's going to be what? You are expected, just look at the word and it's expected to mention all the three, an indicator, and then for this second one, you are expected to state what the endpoint, which means if I say methyl orange, I'm going to have reddish orange. If I say methyl red, I'm going to have pink. If I say naphthalene, I'm going to have colorless solution. So that is that about that. So the last one, which is the balance, okay, second to the last, the balance equation. I've already done that here. That's the first thing I did, so I had to explain something for. This is Roman figure 3 here, the balance equation. Is the reaction between what? Strong acid and strong base here plus to give acid and base, to give salt and water. So this is acid plus base to give salt and water in ratio 1 to 1. So there's already balance. Then the last one is calculate the what?